Good morning, everyone. Welcome to the second day of the Xendee University Week. Good morning to the West Coast people and East Coast people in the United States. Good afternoon in Europe, and maybe good evening if you're listening from Asia to us today. We have a really nice session here for the next 1.5 hours, which is around new innovative technologies. We have new innovative electric storage. We have heat systems, and we'll start with Tristan Bannon today. He's with CellCube. CellCube is an Austrian company, and Tristan is the Chief Commercial Officer of CellCube. Tristan leads CellCube's global commercial strategy, overseeing business development, project origination, strategic partnerships, marketing, and external affairs. He works closely with customer investors, policymakers, and industry stakeholders to accelerate the adoption of long-duration energy storage, and I believe that's the topic today that he will talk about, and advanced solutions that strengthen grid reliability and energy resilience. His expertise spans both technology and policy, with a particular focus on the intersection of energy infrastructure and national security. Over his 20-year career, Tristan has held senior leadership roles in the energy, national security, and technology sector, including serving as Executive Director for Resilient Energy Infrastructure at Leidos Engineering, where he led strategy and delivery of advanced energy infrastructure solutions worldwide. He holds degrees in computer science from Johns Hopkins University and the University of California, Santa Barbara. A very warm welcome to Tristan, and Tristan, the floor is yours.
All right, thank you, Michael. I'm going to do my best to share the screen here, and let's see how this works. All right, can I just get a confirmation that everyone can see my screen?
Yes, I can see it.
All right, wonderful. Well, thank you all very much, and thank you, Michael, and the Xendee team for inviting me to speak today. As Michael said, I'm Tristan Bannon. I'm the Chief Commercial Officer at CellCube. On the next slide, I'll show my contact information, so you can reach out after this. But what I'm going to talk about today, as you can see here, is a bit of a long-winded title: No Longer Storage Technology of the Future, an update on real-world vanadium flow battery projects in microgrid and utility applications. And what that means is I'm going to spend a very brief period of time talking about my technology, the vanadium flow battery, which CellCube makes. And then I'm going to show a bunch of projects that we are building currently, have commissioned, the point of which being to demonstrate that these long-duration energy storage systems, which maybe some of you are very familiar with, maybe some of you will be learning about for the first time, have a lot of features, a lot of benefits, and are really an exceptional technology to accelerate the energy transition we're going through today. You can see my information there. I am today based in Washington, D.C. If you reach out to me on Friday, I will be based in Vienna. That's going to be my new permanent duty location, as I am working with the CellCube team, and we do our manufacturing for our batteries there. There's a QR code here. Feel free to take a picture of that. That'll be a link to a 3D model of our battery, so you can kind of play around with it, zoom in, zoom out, see all the parts. So without further ado, I'm going to tell you a little bit about CellCube first. Like I said, they get some projects. So this is CellCube Energy Storage. So we make vanadium flow batteries. And I'll explain a little bit more about what vanadium is here shortly. But the things I want you to take away is that this is an electrochemical battery. So just like any other battery, it charges from the grid or from renewables or any other power generation source you have, stores that battery, that power, and then discharges upon command. There's a few really interesting and unique things about the battery, though, which have really kind of led to, in the last few years, a much more rapid adoption. We fall into a class of battery called long-duration energy storage. And so our battery in particular has the ability to store and disperse power from relatively short periods, like 2 hours, up to as long as 24 hours. Part of that is because, as you can see, this nice picture we have a modular battery design. So those top, it's a 2-story battery. The top part, that's where we actually have our battery itself. That's the cell stacks and the battery management system. These bottom units are where we keep the liquid electrolyte. So we store our electricity in liquid electrolyte. It's made of vanadium, and we basically flow the electrolyte from the bottom up to the top to charge, and then we flow it back down to discharge. A bit of an oversimplification, but that's why it's called a flow battery. And that allows us to sort of independently scale the volume of electrolyte we have in the bottom. So you can get longer durations with more of this, or you can get more power with more of the power units up top. So it's pretty cool. You can scale it. We have applications that I'll talk about today that are as short as 4 hours. We also have some that are as long as 20 hours. But the really cool thing about having your energy stored in a liquid electrolyte like this is that it is not flammable. So our batteries don't catch on fire. There's no thermal runaway. They are not bound by restrictions from the NFPA or Unified Facility Criteria, if you know what those are. And we can site these batteries directly next to buildings, next to petrol stations, next to ammunition depots. We've got examples of all of those. So it gives you a lot of flexibility in siting things when your battery doesn't catch on fire. The other really cool thing about the battery is that vanadium flow batteries do not degrade with cycling. And so we can run a battery for 20, 30 years. We'll warranty it for 30 years, cycle it a couple times every day, and it will work just as well after 30 years as it did after 1 year. So you don't really have to replace it very often as you do with other lithium batteries and the like. It also works in a really wide temperature range. We've got examples in very cold places I'll talk about, down to -40, in very hot places over 110 degrees. For my friends in Europe or who use centigrade, that's about -40 C to, I think it's about 43, 45 C. The other really cool thing, and this is maybe a bit unique to CellCube, is that we have no Chinese components in our supply chain, no components from other foreign entities of concern. That's a big deal in Europe. It's also a really big deal in the US. And we are one of the rare batteries that can say we are fully independent of China. Ergo, we can qualify for the max investment tax credit and other requirements that have been levied on supply chains. And then kind of rounding this out, fast ramping, we can respond in less than 5 milliseconds. We also have been certified for use by the military, US military. And I'll talk more about that, but it's a pretty extensive qualification the battery went through. So beyond that, the company itself, now I've told you about the technology, the company itself, we've been around for 25 years. We've had our longest battery in continuous operation for over 15 years, working at a utility test facility in Austria. And we've deployed over 150 systems, really in every environment. Yeah, we've got batteries in every continent except Antarctica. What I'm going to talk about today are really our megawatt hour scale batteries, some of our newer models and the applications they're in. So if you all heard any of that and you have any questions, please put them in the Q&A and I'll do my best to address them at the end. Here's a picture of our headquarters, pretty cool place. We have the ability to basically max out our capacity up to 1 gigawatt hour per year. We're not operating at that capacity today, but we do have that sort of bandwidth. I did want to say just a quick word about vanadium because I've used that word a couple of times. Vanadium is it's element 23, so it's a relatively abundant element universally. It's across the pretty dispersed across the Earth's crust. It is not a rare earth element. It is non-flammable. We source it locally for US and European projects. It's pretty common in steel strengthening and defense applications. And basically the vanadium and the vanadium prepared to the recipe that CellCube developed is really sort of the secret behind a lot of the performance of our batteries. So what I'm going to do, I'm going to go through our 3 core markets. They are defense and critical infrastructure. They are commercial and industrial, and then utility. And I'm going to just talk a little bit about each one, how we go to market in them. And then I'm going to talk about and show you some pictures of some projects that are in the ground or soon to be in the ground. So I'm going to start off with defense and critical infrastructure. Really, this is an area that's been growing very quickly for us. This is really focused on U.S. and European installation energy resilience, helping our clients in those communities be able to island up to 14 days off the grid using our battery, microgrid, and distributed energy resources on site. We also do a lot of work that have similar requirements with hospitals, with airports, seaports, rail, things of that nature. And I'd really like to highlight, I kind of mentioned earlier, we have been certified by the U.S. military. And what that means is we went through a process with the Department of Defense starting in about 2023, where they have essentially prototyped an energy resilience project using CellCube's technology. Frankly, this is how I ran into CellCube in the first place, working on this project with their microgrid design partner. And then I was so impressed by it, I actually came over to join CellCube directly. But we've deployed a battery now, and I'll show you a picture here in a minute, to a Marine Corps base in California, fully integrated it with a microgrid and with on-site DERs, and proved out that this technology, it works the way it says it's going to work. And now the U.S. Department of Defense has basically certified CellCube to be procured across the Department of Defense, all the military services, and we're allowed to scale it now. No further competition is required. Any DoD element can just order them on a sole source basis. So it's a great validation we've gotten, and it kind of proves the technology is as good in the hardest applications as it is in some of our other more straightforward ones. So with that being said, I want to show a picture here. So this is the Marine Corps product I just mentioned. This is at the U.S. Marine Corps Mountain Warfare Training Center. It's on the eastern slope of the Sierra Nevadas in California. It's a pretty cool place, pretty remote place. They get up to 700 inches of snow in the winter and some pretty severe wildfire risks in the summertime. After one of those snowstorms essentially took out the grid for about a month, and their two on-site diesel generators proved to be unreliable. They kicked off this project, and we've put about 5 megawatt hours to date. You can see it there, integrated with some switchgear and an inverter. And there's an option they're going to execute here in 2027 to expand that, basically double the footprint to 10 megawatt hours, be able to cover 100% of the critical loads and the non-critical loads on base. We had a cool role in that. We got to be essentially the general contractor. So we led all the design, the construction, the grid interconnection, as well as the battery. And we worked with a couple of partners, including EPRI, the Electric Power Research Institute, Leidos Engineering, who was our design agent, and a subsidiary of Quanta Services called Patelco. So cool picture. And if you're ever in the area, they love doing tours. Here's another project that we just started earlier this spring. So this is with the U.S. Air Force now, and this will put a battery at Hill Air Force Base in Utah. It's a 500 kilowatt, 3 megawatt hour battery. And what's interesting about this one is it's really meant to demonstrate, obviously, the technology itself, but a new kind of a business model. And that is taking the battery and actually delivering it through the utility, which provides service to the base. Many of our clients in the U.S. Department of Defense have privatized their on-base utility infrastructure. And so this is a way for third-party capital to be deployed to get energy resilience within the fence line. And so we're excited to be a part of that. And we should have that battery fully commissioned and online in the first quarter of 2027. Here's another one. This is a really cool project. I've had a chance to actually be at the site there. This is not my picture. I took it off the internet. It's a location I can't really talk too much about, but it's pretty cold. And it's in the Arctic. And this is an extreme sort of an island situation where there is no grid connection. And in the wintertime, if the power were to go out, if the power plant shuts down, they really have no way of getting it back online for 1, 2, even 3 days. So we built a custom version of our battery, which deploys power essentially nominally for 20 hours. And we're doing 8 megawatt hours in the first tranche inside a hangar, which isn't currently being used. And we've got an expansion path that will take that and take it up to about 100 megawatt hours, provide this full backup for the entire base. This is a really complicated project. It's in a place that can get down to about negative 70 degrees in the wintertime, with winds that can exceed 200 miles per hour. Storms can come out of nowhere. It's a really challenging place, but it's a really important place for monitoring threats of intercontinental ballistic missiles. So it's a really important project we're happy to be a part of. And then here's what I mentioned. I mentioned that hospitals are a big part of our portfolio here in this critical infrastructure space. We've got a couple of hospital projects. I'm just going to highlight one today. This is at a hospital in South Carolina, so you can see 3 of our sort of nominal 8-hour batteries stacked side to side there for a 1.5 megawatt, 9 megawatt hour project. This is kind of cool. This is actually being delivered through an energy as a service project with our partner Enfra. And what we like about that is they have found a way, and it's I think a growing demand signal we're seeing across our portfolio. But they've really found a way to use the longer duration the battery is capable of providing to monetize demand charge avoidance, to leverage solar that they're also installing, peak shave, and at the same time provide that energy resilience for medical emergencies. And hospitals have a pretty strict no lithium policy, so they need something they know works, that they can get on base or on the facility there and use quickly. So this is one of a couple of projects in the hospital space that we've got commissioned in operations. The other one is in Indiana. So I've talked about defense and critical infrastructure. That's a community that really values resilience, and that's the primary kind of forcing function for them to make decisions. As I move into our portfolio and some of the new projects we've been doing in commercial and industrial, what I would characterize here is it's really a mix of energy resilience and economic value. They need to be able to continue their operations in manufacturing, in logistics, in compute, even in sports. But they can't do projects that don't make sense economically. And so leveraging tax credits, leveraging utility incentives, and really leveraging the ability to firm solar and to reduce power bills is a huge discriminator here. So I'll show a few projects that we've got going on. This one is in Chicago, greater Chicago area in Bolingbrook at the G&W Electric facility. They're a major manufacturer of switchgear and reclosers and other utility equipment. And I could talk for a long time about this. In fact, I just did a webinar like 2 weeks ago on this project alone. What's great about this one is there are some really interesting incentives and rebates that are available in this territory. So in addition to the federal ITC, which the CellCube battery does qualify for, the state of Illinois has an incentive program. It's actually a rebate where you can make up to $250, or you can receive $250 a kilowatt hour off your purchase price. So for a 2 megawatt battery, actually I have a mistake on here. I don't know how that happened. This is it's a 2 megawatt, 11 megawatt hour battery. You can get $2 million back right away. And then this battery happens to be sited in PJM territory. And with frequency regulation, some changes they've made to the signal there, this battery being operated by an aggregator we work with called Intelligent Generation, they fully paid off the system in 3.2 years. And we're working with lots of other CNIs in the space now who are seeking to replicate that because the economics are so advantageous right now. We've had this battery installed since the first quarter of 2023. So as we enter our 4th year, we are seeing actual slight improvements in the round trip efficiency as the battery has kind of gotten into an operating cycle, and they found ways to use it to play the markets about 23 hours a day, but reserve, I think, 60% of the battery for those resilience events, which is really the genesis of it being built in the first place. I'll go a little bit more quickly through these. So refrigerated logistics is a big one for us where, especially in Europe, the cost of electricity is pretty substantial. And when you have operations that require really 24/7 loads, like a refrigerated facility, the ability to take pressure off that off the grid and also to help them electrify their fleet was a big genesis of this project. Looking back to California, demand charge avoidance is another big one. I'm sure many people here do work in California or know folks that do. Some of these demand charges, the windows are becoming extensive. I mean, there's a time of use tariff for Southern California Edison. These critical peaks are lasting like 5+ hours. And so the ability to go off the grid and to pull entirely from on-site generation during those periods really changes the economics pretty substantially. So we've done 3 projects now with Applied Medical in Orange County, and with more on the way, really leveraging on-site solar and a long duration battery to get them off the grid and to lower their power bill. A new area that we started working in is these net zero stadiums. So this is one that happens to be in our hometown of Vienna, Austria. We're building a battery that will firm up a whole bunch of solar they're building to make Ernst-Happel-Stadion basically the first net zero stadium in Europe. So that's a cool project. And if anybody ever wants to come out and visit our factory, we'll take you downtown and show you the stadium and the battery we have there as well. I'm going to round things out with utilities. I want to make sure I leave a couple minutes for questions at the end. Utilities are really driven by front-of-the-meter applications. So we got a mix of pilots led by utilities as well as independent power producers. And I'll just show 2 real fast here. Here's a project that we had commissioned in 2024. This is for a utility in Brazil called Coppola Electric. The point of this was to do ancillary services, front-of-the-meter, and support grid forming and black start. What they actually wanted to do, they wanted to pilot a vanadium flow battery next door. You can't really see it behind there, but next to a lithium battery to compare the performance side by side and really see how a vanadium flow battery with these long durations, how it could respond to signals and to inflections in the voltage. And entering the 3rd year, the feedback is so strong. It looks like we're going to be adding a couple more pilots down there in Brazil through the same EPC and sister utility of this, as they are seeing the value you can add and seeing that it's actually a pretty reliable system. And then one more. This is a recent project we commissioned in Hungary. It's a front-of-the-meter. Basically, it's an IPP with a large solar farm, and they've added our battery now to provide some additional services there. It's a 1 megawatt, 4.5 megawatt hour project. We just commissioned it earlier this year, and it's I think it's performing better than expected so far. As the weather has improved, the solar is providing a lot more power in the summertime than it does in the winter. We're getting really good data off this. And I'll be doing some site visits actually next week while I'll be out in Hungary. There's an international flow battery forum event happening in Budapest. So anybody who's going to be out there, drop me a line and we'd be happy to show you this project site if it's something you're interested in doing. All right, so that's the quick and dirty. I think I only had 30 minutes, so I ran through a lot of things. I'm happy to share the slides later on with anybody who wants them. But please feel free to reach out if you have any questions, and I will. I'll come off the screen here and answer any questions.
Thank you, Tristan. This was very impressive, and I'm really impressed on how CellCube actually expanded in the United States and got also the DoD approval. I think that's a big achievement. I mean, that's big. We have more questions probably than we can answer, but I will start just as they came in. So the first question, Tristan, is why would any application still use a lithium-ion battery given your indicated advantages?
It's just that's a leading question. Did you write that one yourself, Michael, just for me?
No. It's from Greg. It's not from me.
Yeah. So I mean, I think vanadium flow batteries essentially can do anything that lithium can do. We have tested just about every single use case side by side you can imagine. There's none where the performance is inferior. The only one that we tend to look at is vanadium flow has a slightly lower energy density than lithium. So when you have like a really constrained space, but you're no limitations from your fire, a lithium battery can provide a little bit more compaction inside of that footprint. And then we can get into the economics. The economics are really, really strong if you're going to own and operate the battery for basically more than 12 years. If you're gonna build it and then sell it immediately, there are different factors that kind of go into a financing strategy. But whoever asked that question, that's a much longer discussion. I'm happy to have it with you. Feel free to reach out and we can get into it.
Thank you. Another question: does CellCube offer equipment only, or do CellCube also operate as a turnkey supplier that provides design, procurement, installation services?
We're a battery company. We sort of default to go system first, but what we found is sometimes the best way to get a project off the ground is to expand the scope we're willing to do. I showed you a couple of projects there that we did as turnkey, where we were responsible for essentially from inception through commissioning and continued operation, including construction, including integration with the AC system, transformers, including adding PV. If it gets a project off the ground, we're happy to take a look at taking on more scope. And we've got a few commissioned today. We did that, and a few more in the pipeline. So the answer is yes.
Okay, I think I have one last question, then the rest we'll submit over to you. Okay. At what rate are your non-lithium batteries replacing lithium batteries worldwide? So I think the question is how fast are you growing here?
Well, I'll say this: our order intake for this year is on track to be 15x what it was last year. Now, lithium is a pretty big market, right? I don't know that they see vanadium flow as a threat yet. My team and I are doing everything in our power to change that dynamic. But really, it comes down to education, letting people know that's out there. We started using the Xendee tool really this year. Because it's been extremely effective at visually as well as with data conveying the technical economic advantages of a vanadium flow battery. So Michael, I don't know if Adib's out there, but you guys have been great to work with. Doing as many webinars like this to let people know the technology is an option. I think where we're seeing the biggest growth trajectory right now is in the US and in Europe. The US because in order to qualify for the investment tax credit, you can't have batteries with foreign entity of concern entanglements in their supply chain. So that's really changing the economics of lithium as we head into 27 and 28. And then in Europe, there are also similarly lots of desires for non-Chinese European kind of manufactured systems. So, but we also have projects in the Middle East, in Africa, in Australia, in South America. So it's a good, exciting place to be right now. But part of my job is just to go and tell people this thing exists and why it's great, and then show them the numbers, and then the products come together pretty quickly.
Great. Thanks for taking the time, Tristan, to present here. And now we are moving over to Michael Zellinger. Michael Zellinger is working with Autonomize. It's also an Austrian company, and we're not talking about the heating side of things. And Michael is the CEO of Autonomize, and it's an Austrian energy service provider and planning partner for holistic energy solutions. He supports companies in analyzing energy demand, identifying efficiency potential, and developing integrated concepts for sustainable heat and energy supply. His work focuses on the practical decarbonization of energy systems, combined structure planning, implementation support, and renewable heat solutions, such as solar thermal energy for commercial, industrial, and district heating applications. Thanks for taking the time, Michael, and the floor is yours.
Thank you. Thank you for the kind introduction. and thanks for having me. I'm going to share my screen. Yeah, so you should see my screen right now.
Yeah, I see it.
Perfect. So today, I will talk about not about the electricity, but about renewable heat. Um, Um, and I would like to share practical examples and the structured approach for switching to renewable heat supply with particular focus on process heat and solar thermal integration. So I will jump over this. I guess you will get the presentations, and this is about me and how I get to the company where I'm now, which is much more important. It's Autonomize, and we are a partner across the full journey from analysis to implementation and optimization of renewable-based energy systems, and with a particular focus on heating systems. And we always start with one on-site analysis with load profiles, processes, and the identification of efficiency potentials. Based on that, we develop energy concepts and assess technical and economical feasibilities. We also support the implementation, planning approval, and financial pathways. And after that, which is crucial, we support in the monitoring and optimization phase, because this is very important when it comes to long-term performance. And so the best practices always starts with structures from analyze over design to implementation and optimization. And our projects are very widespread, from housing, farms, district heating systems, municipalities, and industry projects. So when we talk about heat transition, we first need to understand where heat is actually used. And heat is literally everywhere, in buildings, in industrial processes, in agriculture, in district heating network, and hot water systems. So yet these applications differ significantly in terms of temperature level, operating hours, and energy demand. And that is exactly what makes heat transition challenging. There is no single solution that fits all application. That means the starting point should not be a technology preference. It should always be the actual load profile, required temperature level, the operating hours, and site constraints. And in the most cases, best results and best practices does not come from one single technology, but from an integrated combination of efficiency measures, renewable heat storage, and implementation support. So the key point is heat transition is an operations topic and not just a technology topic. To understand why the topic heat is relevant, it's important to remember that heat accounts for a major share of the total energy demand. What you see here in this pie chart is the energy demand of Austria in Europe. And we see here that heat is almost half. 1/4 is electricity and 1/4 is transport. And this picture is in all European countries the same. At the same time, the share of renewable energy in the heating sector is still lacking behind electricity. This is in Austria. We have here about 75 to 80% renewable in the electricity grid, but only 35 to 40% in the heating system. This makes heat supply one of the biggest levers of decarbonization. In other words, if we want to decarbonize energy systems, we must decarbonize heat. And this is where solar thermal becomes especially relevant. Solar thermal systems create value where heat demand, temperature level, and available surface area fits together. For lower temperature levels, between 30 and 90 degrees Celsius, it's 80 to 190 degree Fahrenheit. Solar thermal heat can be used directly as a heat source, for example, in domestic hot water systems, for washing, for cleaning, for process water preheating, can be directly used. For medium temperature heat, between 90 and 150 degrees Celsius, so 190 to 300 degree Fahrenheit, it can be used as an additional heat source in combination with other heating systems. For example, in drying processes, in textile processes, in food processes. But in most cases, solar thermal works best not as a standalone solution, but as a part of an integrated hybrid energy system. And in combination with, for example, heat pumps, peak load backups, storages. So the main message here is solar thermal is strongest when there is recurring heat demand meets sustainable temperature level and available areas. And when we talk about solar technologies, it's always important to focus on the target energy form. If the target energy is electricity, PV is the natural reference. But if the target is heat, solar thermal can deliver a very high useful energy yield per square meter. From our 1000 watt per square meter, which are available at the Earth's surface, we can harvest around about 60% with solar thermal systems and 20% with PV systems. So there is a factor of 3 in performance per area. That's why solar thermal deserves, in our opinion, a place in the technology mix whenever a project is clearly heat driven. And this is a practical roadmap how we analyze our projects to switch to renewable heat supply. And it always starts with analysis to understand the heat demand, the load profile, the temperature level. This is crucial before deciding a technology. The second step is to identify the application where renewable heat can create the most value. Then the development and integrate of an integrated concept with the right technology mix and a realistic financial pathway. So the project needs to be bankable. And the fourth step is to assess the feasibility. So are there enough available areas, the storage, the hydraulics, economics, approvals, and the last step, the implementation, which is followed by monitoring and securing of long-term performances. So not every site is equally suitable for solar thermal or for decarbonizing the heat. So project selection matters. And good project usually starts with suitable roof or ground areas and a good solar access. This is crucial when it comes to solar thermal integration. It also needs a matching load profile. Ideally, a stable heat sink with daytime demand, summer demand, or both. And the required temperature level must fit, as mentioned before, so that solar can economically deliver within the overall system concept. And finally, the integration matters. So the storage, the hydraulics, the system design, these are all key indicators what turns solar yield into useful and usable heat. And typically good archetypes include process of water, cleaning, washing, daytime operations, summer heavy demand, and expandable energy systems. So I brought two use cases, two different use cases of projects we did the last year. The first case study is a district heating network in Austria. It's rather small district heating system with two biomass boilers with a capacity of 850 kilowatts for winter and 350 kilowatts for summer and peak load, in combination with smaller buffer storage and thermal storages. And this system supplies more than 50 buildings and operates throughout the whole year. So they supply the district heating system also in summer for hot water, but the major energy share is of course in winter. So the goal was not only to reduce the biomass consumption, but also to improve summer operation and increase the share of renewable heat through solar thermal integration. What you can see here is the overall layout of the system. The solar collector field is located next to the existing boiler house and connected to the thermal storage system, which is here indicated in blue. And the additional storage system, which comes with the solar thermal plant, was an important part of the concept, as it allows the solar energy to be shifted and utilized more efficiently. And we have here a supply and return temperature in the district heating grid of about 80 degrees Celsius supply temperature and 48 degrees Celsius return temperature, which are common temperatures in our district heating grids in Austria. And what you can see here in the table below, that the major share of energy used is during winter time, but there is still a lot of energy used during summer for providing hot water. And this system needs around about 2,000 megawatt hours per year of energy. I will jump over this. Here you can see how the system is integrated into the existing district heating network. It's connected through the thermal storage, where during the summer, the solar can cover a significant share of the demand and reduces the boiler operation, the biomass boiler. And during winter, the biomass boiler remains the primary heat source, of course, while solar is contributing whenever conditions are favorable. And here in this hydraulic integration, the collector field is connected via this heat exchanger to the existing system and to the storage. And this collector circuit is filled with water glycol mixture for freeze protection. So we have here freeze protection in the primary circuit. And what is crucial here, or in those systems, is that we have a good stratification inside the thermal storage tank, that the temperature, which is varying over the day from the solar thermal field, can be used in the best way and can be feed in the right height of the thermal tank. Here you can see the installation of the support structure, and these are mainly steel bars which are rammed into the ground, And it's a very lightweighted support structure because the solar collectors we used are flat, large-scale collectors with a size of 6.6 feet times 20 feet. So it's one collector, and they are very stable. So they need only a lightweighted under construction. Here you can see such a collector. So it's like 5 times of a PV module. They are connected in the field and then connected to the underground piping. And each collector field, what you can see here in the right picture, is equipped with balancing valves, which are allowing the flow to be distributed evenly across the entire field. And this ensures that all collectors operate under the similar conditions and achieve optimal efficiency. The project was commissioned approximately 1 year ago. So we have a lot of data of the project. And one key innovation there was the implementation of a predictive control system. And this is, instead of reacting only on the current operating conditions, the control system consider forecasts of demand and expected solar generation to optimize the system operation. What we do is we use it to determine the required storage capacity for the solar energy. By anticipating the solar gains and the heat demand, the storage can be managed more efficiently and increase the solar utilization and reduce, of course, the biomass consumption. So what you see here is the forecast. The controller gives the biomass combustion that he needs to. He can also only use 20% of the storage volume, and the other volume needs to be unused for the biomass boiler and needs to keep free for the solar system. And the objective here is not a perfect prediction, but even with moderate forecast accuracy, can make a significantly difference when it comes to improvement of solar integration and unnecessary boiler operation. And we put together the measured data, and you see here 2 weeks, and the orange line is the biomass boiler, the energy from the biomass boiler. The blue line is the output of the solar system, and the green is the percentage in the storage tank. And you can see here the first 3 days the biomass boiler is still needed due to higher demands from the grid, and at the same time a reduced solar thermal output. But after 3 days, the solar plant could cover the whole energy demand on its own, and the biomass boiler shuts down for a couple of weeks. Without forecasting, the boiler would fire up almost every morning, because the control system only sees the current storage temperature and reacts accordingly when a specific threshold is reached. The biomass boiler fills up the storage. With the forecasting, the system knows that solar energy will be available within the next few hours, and the biomass boiler can safely wait. And this avoids unnecessary boiler starts and allows the solar thermal system to cover a large share of heat demand in summer times. The second case study comes from agriculture, and this site combines poultry production, so chicken, with drying application, drying of wood chips and feed, and both processes requires significantly account of heat. This making these use cases interesting for renewable heat integration. And this poultry farming presents a challenging operation environment. They need a large amount of fresh air for animal welfare, while at the same time stable temperatures must be maintained at floor level. And this results in a relatively constant heat demand profile through the production cycle and through a whole year. And such farms in Austria usually have 40,000 broiler chicken, and the energy demand of one such farm is about 500 to 600 megawatt hours per year. And most of them already have existing PVs on the rooftop, which totally makes sense because of what you see here is the electricity demand over the whole year, so from January to December, because they have this huge ventilators. They need to put fresh air, so they have also high electricity demands in summer. But compared to the heating demands, it's not that much. And this is a typical product cycle of 5 to 6 weeks, where the heat demand follows the poultry production cycle. The demand is highest at the beginning of each cycle and decreases as the animal grows. And to understand this is essential for sizing renewable heat systems and storage correctly. And in between these cycles, the energy can be used perfectly for drying processes, as in this use case. And there was an integration of additional thermal storage tank with around about 24 cubic meters. So it's about 6,600 gallons of capacity. The concrete core was activated by thermally activated, and we have here solar yield of 550 kilowatt hours per square meter in year, and solar fraction of up to 50 to 60% in summer times. What you see here is how the different heat consumers are connected, and so the combination of the poultry housing, the drying processes, the thermal storage create multiple opportunities to utilize solar heat efficiently throughout the whole year. And I will finally give you some key facts about solar thermal system. We have a thermal output, as I mentioned at the beginning, of around 60 watt per square feet, and which is important when it comes to economics, are the investment costs. And we have here investment costs approximately of 300 euros per square meter. So it's just roof mounted and not connected. So it's 430 euro per kilowatt peak. And installed, commissioned, integrated, 720 euro per kilowatt peak. And a yield of 46 to 60 kilowatt hour per square meter, per square feet and year. And which is interesting are the levelized cost of heat. And when we calculate it without any subsidies over a period of 20 years, while those systems have a lifetime of more than 30 years without any problem, we have here 32 to 35 US dollar per megawatt total costs of the energy out of the system. So one or two key takeaways. It's always start with heat demand, not with technology. This is always important. And solar thermal is strongest when it's integrated in a broader system and it's combined with other systems. Thank you.
Thank you, Michael Zellinger. We have a couple of minutes left here. One question I want to take here is the solar thermal system that you're using fixed, or you have tracking system? I guess that's the question here. And is shading an issue?
No, it's fixed. We have no tracking system. They have the highest performance if we have an inclination of 30 to 40 degree in direction south. Shading is not that big problem as it is in PV. So if we have a shading, or if we have fractional shading, it's not that big issue.
I guess it's because of the thermal latency of the system, right? Because the system responds slowly. Okay, that's what I got it. Yeah. Another question here. Maybe we missed this, or I missed it, but how much biomass are you substituting with this system? I mean, can you remove 50%? Is it 25%? I mean, how much of the regular heat fuel will be replaced here?
Yeah, it depends on the system, of course, but the most efficient systems remove or land that they are suitable for summer load. So they move the summer load with 80 to 90%, but then it's an overall fraction of 30 to 40%. So 30 to 40% of the total energy comes from solar.
Okay. And I have a personal question at the end, because as people maybe hear that, I'm also a native German speaker like Michael Zellinger here. So I mean, is the Austrian government changing subsidies on this? Because we all know that PV and all this is very important for all these governments, right? But is the market changing now? Because it's a no-brainer to do solar thermal, right? But is it still the same thing like it was a couple of years ago, right?
It's still the same, and funding is crazy at the moment, because it's changing every couple of months. So this makes it a little bit hard for companies to invest in renewable technologies, because the funding system is changing so often. I hope that there will be more continuous funding in future, but yeah, I'm not sure.
Okay. Yeah. Okay. But it's a great technology, and it seems like it's cheaper than just doing this through photovoltaics in some cases, right?
Yeah.
Okay. Thanks, Michael. So now we're coming to the last, but not least, presentation today from Nick Bustamante, and he's with Exowatt. And Nick Bustamante is the Chief Data Center Officer for Exowatt. Nick has more than 25 years of global hyperscale data center development experience in over 100 markets. He's responsible for all aspects of development, operations, and business globally. Nick's background includes leadership positions at core scale data centers, Apple, Google, Microsoft, and Rackspace. He holds numerous industry certifications, has co-authored an array of industry standards. So Nick, I already heard a little bit about your technology, and it's very cool. So just welcome, and the floor is yours.
Thank you, Michael, and thank you, Xendee, for asking us to participate in this and welcoming us. This has been a really compelling, hour or so. Let's keep this going. And so we're going to talk a little bit about Exowatt and what we're working on. First off, I want to talk a little bit about our mission statement, right? So we're trying to make energy that is sustainable, that's renewable, that is always available, and we say almost free, right? We would love to build a system that was completely free, but we are a business. And so we are building a system that is very doggedly chasing unit economics down to as low as 1 cent per kilowatt. We'll show you how we achieve that, but this is our goal. This is a system that we have been deploying since around 2025. Significant traction with our product, significant pipeline that we have developed and are continuing to deliver against. We've raised quite a bit of capital also. As an aside, we are still a private company, but continue to raise capital, and recently went through our Series B round as we continue to develop the platform. If you look at our website, you'll see that we've got the exowatt.com website. There's a section in there called Exorise. So I'm also the general manager of Exorise, which is where we go to kind of full turnkey solutions for our products. And these are potentially projects where we have not just a demand for energy, but also demand for maybe something else like a data center or something like that. So why are we looking at talking about Exowatt today, right? We've got this massive gap that everybody is aware of in the United States. We'll focus on the United States for this discussion, but really broadly, globally, right? Significant energy gap. Total U.S. data center demand, right? It's even challenging to get to accurate numbers, right? When we look at, say, my home state of Texas in the United States, sometimes people will look at the kind of ERCOT queue. This is the energy council that oversees the grid in Texas. That number is somewhere between 400 and 500 gigawatts, depending on who you ask. But just announced projects in the United States, and data center specific. Again, I'm a data center guy. We're talking about 222 gigawatts, right? So we've got this significant pipeline of data centers. I'm sure this number is significantly higher today. This number is about a quarter old, and this number continues to grow very, very rapidly. And then we have high confidence projects, right? These are confident projects with utilities who've come back and said, we can deliver that, or we are planning to deliver at still almost 150 gigawatts of capacity. Significant power has to be deployed for that. And now we've got this gap. We've got this time to power gap as a result of that deficit that's going to take years to fulfill. We typically see in kind of power hungry markets, right, where there's already a significant demand. Tier 1 markets, these are places like Northern Virginia or Dallas, Texas, 3 to 6 plus years in the queue just to interconnect. And then significant constraints around supply chain, critical equipment like transformers, like all of the transmission systems that one has to go procure to distribute energy in the conventional grid sense has a long lead, right? Right now, high voltage transformers in the United States typically taking around 5 years. We also see a large focus on geopolitical threats. Most of the transmission systems that we buy in the United States and also abroad are relying on constrained materials or relying on the procurement of components or entire systems that are imported. And because of that, and as you've heard the other presenters, we talk about, a concentration in foreign manufacturing, and there's significant exposure there, right? Not just on tariff and trade, but also from a national security perspective, there's concerns. So those are all some serious bottlenecks. But the data center product and what we work on typically at Exowatt and Exorise, we see a significant community backlash, right? This is not news to most folks. A lot of concern about data center NIMBYism, not in my backyard. Do we have the right say and the right voice in what's going on with our development? And a lot of the focus there is on power. How are these large power using data centers contributing to the rates for everyone? And in fact, there's been a lot of discussion about if that's really happening or not. That aside, there are some data centers who are then going and saying, well, because I can't get all of the interconnect things engineered fast enough because there are constraints with my utility around their supply chain and their delivery, I'm going to go provide my own energy and go do something behind the meter. And typically in the United States, folks are relying on natural gas for behind the meter. So that introduces yet another concern. Are there legitimate concerns around air pollutants, emissions, noise, things like that when we're sitting next to a community? And so we are addressing a lot of those things. We're seeing also this rapid rise in the cost of energy that data center customers are paying. And so we see folks paying up to 35 cents a kilowatt hour for power. And the unit economics around that are incredibly poor, right? They're buying down a lot of the things I just mentioned, those risks, and paying for that. We don't think that that's sustainable. We don't think that using natural gas long term for long duration, years, decades, is perhaps the best way in every market. And so what we're providing is a system that addresses all of these concerns. We'll talk a little bit about manufacturing and scale at a global level. And this is something that Exowatt and its investors are very focused on. Over the last 2 decades, the photovoltaic industry has really optimized this beautifully. We've gotten to a point where photovoltaic panels are 99% less expensive than they were only 20 years ago. And that's primarily been accomplished in China. 85 to 90% of all of the commercial photovoltaic panels in the world are manufactured in China. You've also got the battery industry with it. And so, again, looking at what we are doing at Exowatt, we wanted to optimize around this. How can we bring manufacturing back to the West? How can we bring manufacturing back to the United States? How can we also manufacture this abroad without the use of conflict minerals and materials? And what you'll see in our design is highly optimized for that approach. We primarily use steel and glass and sand to make glass and our battery system. And that's it. We don't use conflict minerals. We don't use chemicals in the process. We use a very streamlined approach. So, why modular, and why dispatchable, right? So what we're doing with Exowatt and what you see on the left side of our screen here are frontal lenses. And these frontal lenses are magnifiers that capture the heat from our nearest star, from the sun. And so we take this heat through this silica on glass panel that we manufacture and beam this into what I like to affectionately call a box of rocks. And so we're storing, again, the energy that we collect as thermal energy, not in an electrochemical system. And so we like to store this heat at up to 1,000 degrees C. We like to kind of float it around 800 C. And then it's dispatchable. As nighttime comes, as evening comes and solar irradiance falls off, then we deploy our battery, and our battery is composed of silica, it's sand. And so we have this heat battery that we use to export up to 120 hours of heat from that battery system. So significant storage capacity there for multiple days, even if necessary. And as a result of that, it's dispatchable. There's this issue where folks want to turn to photovoltaics because the economics around it are really great. You'll hear us consistently talk about in public about unit economics and optimizing on that. We think photovoltaics have really nailed that. Where that falls apart is when we have to come and bring in a battery system, right? And typically that battery system has been a lithium-ion storage system. And you may have heard some of the other speakers talk, right? We've heard about vanadium flow and flow batteries that's going in the right direction. Moving away from lithium ion. I myself in my career have been a big proponent of lithium ion years ago, and then we've moved away from it and started to move, thankfully, as an industry away from it in the data center world because of all of the issues that I mentioned earlier around, lithium, cobalt. Those are conflict minerals, and really just not scalable. And so modular is the way. We build these blocks essentially, in which you see. Here is a 20 foot shipping container. And we can combine these in as many megawatts as we need to. Our kind of standard block, what we prefer is 2 megawatts. And by combining multiples of that, there's no limit to the scale of the system. And we're really proud of the way that the system scales because, again, we focused on unit economics. We've built a box that we can copy and build that in many places. So we're going to go through a little video here. I apologize. I'll probably let this play, and then I'll come back to the beginning of this video and stop. So first we'll watch it, then I'll come back and stop and narrate a little bit. So what you see here is, obviously, solar energy hitting the frontal lens array, and then cutaway of this being beamed into the Exowatt P3 module. And again, scale, so you get a sense of that. This is about 20 feet long. And so frontal lens array on top of it, each of these is about 1 meter in size, these squares. And this is a silica on glass material that we manufacture ourselves. We do this with something called a diamond lathe. And interestingly, there are not very many of them in the world. We've got one of a few in the United States, and we're working to build more of that out. It's a very simple process. It just goes to speak to, again, kind of one of our concerns, which is that true manufacturing and engineering has largely left us in the United States. And so we have a very fundamental challenge here, in that we have to build some of that tissue back up here in the United States to be able to manufacture even just basic thing like this glass panel. These panels sit on top of a single axis tracker, right? So by using this tracker that can switch in a direction here, we are able to gain east to west directional control. We get about 30% more efficiency out of the system by maintaining the optimal solar alignment. And then we beam that solar heat down into our storage system. So as we cut away these panels, you can see some of the insulation. I mentioned earlier that we like to see a system that is around 800 C. You'll see a map here in a few minutes where we talk about solar irradiance. And we like to put these systems into high solar irradiance areas because that lets us start a system up quickly, and it obviously lets us consistently keep that system charged, right, where there's very little, if any, overhead clouds, no shading, things like that. And we'll talk about why we think those are some good areas for development too. But getting back to this, beaming this energy down into this silica substrate, this is what I like to call, our box of rocks. We're constantly studying the details. What you don't see here is the actual composition of this substrate at a kind of an atomic level. We've engineered so that we get very high density in this application. You would think that this box would be super, super heavy. It is heavy. It's several tons, but it's not that heavy for a 20-foot shipping container. This is only about 15,000 pounds completely loaded and configured. And so it's relatively easy to transport. It is a solid state process, essentially, other than the tracker at this point, and it's very easy to construct, to deploy, and to operate. In fact, the only real maintenance, I apologize, lost that slide, is our power conversion unit, which I'll get to now. And so you see the heat cycle here, and over to the right, we have our PCU, our power conversion unit. So our power conversion unit is a Stirling engine. This is, in fact, where we then take that thermal energy and convert it to an electrical signal. And so by using this loop and exporting it through our Stirling engine, we essentially have a closed loop system. We have this helium, what we call air spring in the system, that progresses through that Stirling engine, and then we output through the Stirling engine system. I mentioned a few minutes ago, why we think our system is right for data centers. Well, we think that, and as you've seen, the NIMBYism abroad and in the United States, there are a lot of places that data centers belong, but also happen to have good solar D&I, that have good direct irradiance. And those aren't places that necessarily have a tremendous number of humans in them. And so we think there's good alignment between, hey, let's put a data center here, or let's put a large energy consumer. Let's not worry that there are a lot of people around who are going to complain about it being in their backyard. Our typical data center designs, by the way, don't use water, as do others in this industry, but we still have a need for power. Well, because we're solar, we want to be able to get lots of land, and we want to do that optimally at low cost. So we think that these markets are really the right place. The United States is blessed because we do have a lot of good solar D&I across the United States. But in particular, it's very high in the US Southwest, right? So if we start in Texas and kind of move west into California, we've got a high concentration of areas for great solar projects, which have already started to scale. Texas and California lead the United States in renewable deployments, and they comprise significant portions of the grid there. And we think that directionally is fantastic. And so, we're seeing this significant growth, right, in Southwestern data centers as a result of that renewable story. We see some folks in the industry, hyperscalers like Google and others, who have realized this for a decade or longer. And so they've been procuring power purchase agreements and offtake agreements with renewable power providers in a lot of these markets already for a significant amount of time. And we think that is directionally fantastic. We think that's where the market's going, and we think that there are others who should think about that and potentially go that direction. And as we see the shift, westward, right, with data centers, we think it'll follow that renewable trend, where we have more and more IPPs or independent power producers who are partnering to deliver these kinds of systems, like you see us making at Exowatt and others today. Significant decarbonization with our product too. We think that's a fantastic story. We're very focused on that. I mentioned earlier, a lot of folks for behind the meter are turning to gas because it's fast. We think that not just from a unit economic standpoint, but from a sustainability standpoint, as one does the math, the carbon story there is relatively poor. They look to ways to decarbonize that, and solar is a great natural fit for that. And with that, I have left some time for questions. Happy to take questions.
I need to probably unmute myself. Thanks, Nick. It's a great technology. And we have a couple of questions. I mean, there's one which you see on your side, and I think you're just taking care of that by yourself, right? There's a question, what's the square footage required for a 2 megawatt system?
Yeah, we like to see a few acres for that system. It really depends on the market, but if we're in a high solar D&I market, it's going to be 4 to 4.5 acres. That's including storage, right? So obviously solar is a kind of what I'll call low density power system. It's not a nuclear generator. We need space to be able to lay our panels out. But with our system, we've also got batteries, our thermal storage system underneath it. So about 4.5 acres.
Okay, thank you. So, and there's another question, and it's the same that I had. I mean, you're focusing a lot on data centers, right? But putting data centers aside, are there 1 or 2 vertical markets are use cases which are particularly good fit for your technology? Because I think there might be other markets too, right? I mean,
yes, absolutely, right. So we think about heavy industry and commercial operations, and not just those. I mean, look, I live in Central Texas, and when I participate in city council meetings, even occasionally hear folks who are trying to build a gas station or trying to permit an industrial warehouse that's just going to use a megawatt of energy, and they're in some queue that's going to take them years potentially just to secure an interconnect and build something. If you don't need that much energy, solar is a great product, because if you're building especially something like industrial where you've got a large roof, you can put it there and don't have to necessarily worry about that interconnect any longer slowing you down. We think there's also a renaissance when it comes to folks who are comfortable being behind the meter, and utilities have realized this. And even in a place like Texas, which uses 40 to 50% of the grid as natural gas on any given day, we've got a lot of renewables here. The utilities are coming in saying, well, if you've got dispatchable renewable energy, if you've got a battery somewhere in your system, even down to a residential system where we've seen things like base power, for example, the utilities are incredibly interested in that. So I think, again, I'm a data center guy, but broadly speaking, it's a very interesting, compelling time for this system and for others, because the application really is boundless. Everybody really needs it.
Mm-hmm. So there are a couple of other questions. I have one because you just reminded me to something. And I mean, is there a limitation? Because I mean, if I understand your technology correctly, you're basically linking the storage with the generation unit, right? But could you decouple this so that maybe you can put the solar, the heat generation aside from the storage? Maybe this would open up different markets. I mean, have you guys thought about this, or is this not possible just for me?
Yeah, we absolutely have thought about it. We're trying to produce products that are as solutions so that one can essentially say, hey, I want all of this kind of in, one-stop shop. But we have absolutely, worked with some in the companies in the past who are interested in maybe just the solar collection and solar generation, not as much on the storage component of it, or vice versa. Hey, we need a big cheap battery. We're less interested in a heat battery in the solar aspect of it. And so I do think that's a very active and developing market, and yeah, it is compelling, and it is something we think about for sure.
Okay, so there's a question from the audience. How long does it generate after the sundown? So I think it's about the latency and heat stored in the system. Do you guys have to shut down the generation immediately, or is there a delay?
There's a little bit of a delay. It's a few minutes. And
Okay.
so, it's a short delay. Generally, the system is, if it was, we don't go from day to night instantly. And so because we're able to predict output, usually the system can start to supply from the battery before we actually drop off. And so there's no drop. And so it's an elegant switchover from a demand perspective. There's no drop in power output.
Mm-hmm. So there's a question from John, which maybe is very similar to what I was asking. Can these units be considered for building rooftop applications? What is the unit area of one unit, and what energy output?
Yeah. So altogether, we like to deal in terms of unit output at a hour output. So our most basic system is essentially going to be about 24 kilowatt hours of output. If I look at just raw, output E in terms of electricity output, smallest unit's going to be around 1.2 kWe. And for that system, it's going to be a single 20-foot container. So pretty small, pretty compact.
Okay, another question. For multiple staked units, do you connect all the Stirling generators in parallel, or can it support a larger single generator?
Great question, right? So that is something I actively am working on. Today, our system is connected completely in parallel. I mentioned we have kind of this 2 megawatt block. There's no reason that block can't be larger. At some point, if you're engaged with us, we have a conversation with you about what kind of voltage and what kind of current you like to see. Our system is unique because it outputs both alternating and direct current. And so our kind of default voltages are 480 volt three-phase AC and 800 volts DC. Those are our native voltages. When we get into very large scale applications, and you'll see this, in particular in China, where they're constructing solar fields at 1500 and 3000 volts, we are capable of those kinds of systems. But we think the United States and the rest of the West has really, tended to have a discussion around 800 volts. We are comfortable, though, scaling up on the DC side. On the AC side, large data centers, large power users in the United States have mostly standardized around 34.5 or 35 kV class equipment. Western Europe is in the kind of 22 and 11 kV size. We're comfortable living in that kind of environment as well. So the large scale industrial power environment is what we are used to and what we like to continue to develop against.
Mm-hmm. Okay, and the last question, maybe it's a bit sensitive, but what is the LCOE of Exowatt solar power systems versus equivalent sized battery storage and PV systems?
Yeah. The landed cost of energy for our system is competitive. We think we, in a high D&I market, beat those systems all day, every day. We think that we're able to do that also because of the speed, right? So when you take into consider PV plus BESS, which is, again, what we're addressing, the BESS is really where, the cost and the delay and operation really starts to degrade in comparison to what we do with P3. So we're competitive as much as I'll say. I'm not going to give you a quote here on the online. I would love to. So please reach out if you want one. But we are competitive.
Okay. Thanks, Nick. Yeah, well, with this, I really want to conclude this very interesting session. I want to thank all the attendees, the speakers, and I think we have now a 15-minute break. So you have to get off this Zoom link, and then in 15 minutes, we have another session, which is completely different to this one, which is around small modular reactors. So if you're interested, just tune in 15 minutes on the new Zoom link. Thank you, everyone.